Yeah, it's really hot in here. So let's talk about rates of change. Rates of change. Rates of change. Rates of change. Some notes, and then we'll jump in and do some problems. So rates of change. Rates of change. So we'll let y be equal to f of x. And we're going to define what's called the average rate of change of the function. So the average, this comes up in the homework as well, the average rate, so the average rate of change of the function, so the average rate of change of f over AB is, and this is something that you see in algebra class, except in algebra class they use different notation. They use x1 and x2, which I don't like. I like this class better because I like a and b. It's easier to write a and b. So the average rate of change of f over ab, basically you subtract the y values, you divide, and you subtract the x values. So it'll be f of, and I like to use b, so f of b minus f of a, and then you divide by b minus a, so b minus a. So b minus a. That's it. That's the formula. This is called the average rate of change. So that's it. You can put an a here and an a here and a b here and a b here. You can switch the letters. As long as this matches this and this matches this, you're good. We'll do an example later.
Is that just slope?
Yeah, it's just slope. If it's a straight line, it will be the slope. Yeah. If this was a line, it would be the slope. Yeah, this leads to the derivative. If you take, this is the slope of the secant line, actually. So if you take the limit, you'll get the derivative. Yeah, good, good. In fact, let's rewrite it that way, the way that Logan is indicating. So over x plus delta x. I'm using the delta instead of h. I could have used h. I don't know why I didn't use h. Too late. So over this interval, right, you can rewrite it. It would be f of x plus delta x minus, wow, there's a lot of people here. Wow, what a full class. It's going to add to the temperature. Let's make it really hot. Over f of x. I always think back in the day when this was created, we didn't have air conditioning, right? And then you subtract this, x plus delta x minus x. What cancels here on the bottom? The x's, yeah. So you end up with f of x plus delta x minus f of x over delta x. So this is very familiar, right? This is the slope of the secant line, right? We saw this before. So the average rate of change is really just the slope of the secant line. That's all it really is. If you remember what that was, the idea was if you had a graph like this, and you have two dots and you connect them and you draw a line, that's called a secant line. This is the slope of that line. Right? What we're doing is we're taking the limit of this. And when you take the limit of this, you get infinitely many secant lines and they approach a line that just touches. That's called the tangent line. The slope of the tangent line is the derivative. So if you let delta x go to 0, let's formalize that. If you let it go to 0, then the derivative of f of x is equal to the limit of that expression. So limit delta x goes to 0, f of x plus delta x. I kind of like that delta x. It's more work to write it, but it's kind of fun to do it, over delta x. So we get this. So if we take the average rate of change and we let delta x go to 0, we get the derivative. It has a new name now. Okay, it has a new name. We're going to call this thing, or the derivative, we're going to call both of these the instantaneous rate of change. So f prime of x is now the instantaneous rate of change. So instantaneous, it's a big word. Instantaneous rate of change. Instantaneous rate of change. So the average rate of change is just this over here, right? Or this, right? And then the instantaneous is the derivative. So what is it for? it gives you the rate of change at that particular point, right? It gives you the slope at that particular point. As a simple example, just for intuitive purposes, let's say, oh, it's hot in this room, so let's use this example. Let's say f of t is the temperature in this room. So temp at time t. It's the temperature after t minutes in this room. So you plug in a value for t, there's a formula, and it gives you the temperature, like 80 degrees, 85 degrees, 100 degrees, 120 degrees. So the derivative is the instantaneous rate of change of the temperature. So it will tell you how fast the temperature is changing, right? So if it's heating up, it'll be positive because the temperature is increasing. If it's cooling down, it's going to be negative because the temperature is decreasing. So we'll talk about that later. So this would be the rate of change of the temperature. So rate of change of temp at time t. So the derivative gives you the rate of change of anything, right? Of anything. You have any object, anything, any function, and the derivative will give you the rate of change of that function, right? So if this tells you the population of deer in a forest, the derivative will tell you how fast the population is growing or shrinking. If this is money, it'll tell you how fast your money is increasing or decreasing, right? So the derivative tells you whether the quantity is decreasing or increasing. So it's the rate of change.